Welcome to a new episode of the podcast. Vox Agent is made by AI for business executives that work with AI. And welcome to this deep dive. Today, we're plunging into a topic that's quietly revolutionizing factory floors and supply chains. Multi-agent reinforcement learning, or MARL. We've compiled quite a stack of insights, from industry reports, academic reviews, and some really fascinating case studies. And they all seem to point to how this advanced AI is making manufacturing smarter, faster, and, well, incredibly adaptable.
Absolutely. Our mission today really is to extract the most important nuggets of knowledge for you, give you a shortcut, if you will, so you can understand not just what MARL is, but crucially why it's becoming so essential for business executives, especially if you're looking for that competitive edge. Get ready for maybe some aha moments and definitely a peek into the future of industrial operations.
Think of it as the ultimate team sport for AI, right? Where machines learn to coordinate like never before. It's less like AI playing chess alone and more like a whole team of AIs playing on the same board, maybe. So, to kick us off, what exactly is multi-agent reinforcement learning, and how is it, different from other AI we hear about all the time?
Okay, good question. So at its core, MARL is a branch of artificial intelligence where you have multiple independent agents. These agents, they learn to make the best decisions through trial and error. But the key thing is they're doing it within a shared environment.
Okay, agents. Like what, physically? Robot?
Could be robots, yeah. A robotic arm, maybe a conveyor belt system.
Yeah.
Or even a software service that's managing inventory. Each one is an autonomous decision maker.
Got it. Autonomous.
Right,
Okay.
and what really sets MARL apart is how they learn. They don't just learn based on their own results, their own rewards. They adapt their strategies based on performance feedback, sure, but also, crucially, by anticipating and reacting to what the other agents are doing in that same space.
Ah, okay. So it's less like a lone genius figuring things out
Exactly.
and more like a perfectly synchronized sports team.
Yeah,
Or maybe an orchestra, where everyone's constantly adjusting to everyone else in real time.
that's a great analogy, the sports team or orchestra one, because it emphasizes that coordination aspect.
So how did this, this approach often seen in complex games like StarCraft or Dota, how did it find its way into the, let's say, grittier reality of a manufacturing plant? What problem was it solving there?
That connects directly to the whole push towards Industry 4.0 and smart factories. You see, traditional control methods, they often optimize things in isolation, like one machine, one process.
Right, tune one thing at a time.
Exactly. But modern production systems, they're incredibly complex, interconnected, dynamic. Think about all the dependencies across a factory floor, machine settings, inventory flow, everything affects everything else. These traditional isolated controls, well, they just struggle with that level of complexity and, frankly, uncertainty.
Okay, that makes sense. The old ways weren't built for such connected systems.
Precisely. And we saw early on MARL's potential in other areas. You mentioned games, DeepMind's AlphaStar mastering StarCraft 2, OpenAI's Dota 2 team. These showed our MARL could handle incredibly complex coordination under pressure, real teamwork, but for AI.
So people saw that and thought, hey, maybe this could work in factories.
Basically, yes. It spurred researchers and engineers to apply MARL to manufacturing challenges, moving it from, theoretical concepts in simulations to actual practical deployments. And for that smart factory vision, which is all about mass customization, agility, real-time responsiveness, our MARL isn't just helpful, it's becoming, indispensable for getting all those different parts working together.
Indispensable. Okay, that's a strong word. So here's where it gets really interesting for me. How do these teams of AI agents actually operate in a factory setting? What's going on under the hood?
Right. So practically speaking, each MARL agent in a factory perceives its environment using sensors, data feeds, things like the current machine status, how long the queue is, product quality readings, that sort of thing.
Okay, so it sees what's happening around it.
Exactly. Based on that perception, it takes actions. Could be adjusting a machine's speed, maybe rerouting a product down a different conveyor, or reallocating resources. And then crucially, it gets feedback, a reward or a penalty. And that feedback is directly tied to operational goals, hitting throughput targets, reducing delays, improving quality.
And this happens continuously.
Continuously, learning and adapting. Now, a common and very effective way to structure these systems is something called centralized training, decentralized execution, CTDE.
CTDE. Okay, break that down. Centralized training.
Right. So during the training phase, which usually happens offline, often in a really detailed simulation, a digital twin, perhaps the agents might share information. Often there's a centralized critic function that evaluates the joint actions of the whole team. This helps the system learn the best cooperative policies, how to work together effectively.
So they learn as a team first, in a safe space, basically.
Precisely. But here's the clever part. Decentralized execution. Once they're trained and deployed on the actual factory floor, each agent makes its decisions independently, based only on its own local observations, what it can see right there, right then.
Ah, okay, so they don't need constant communication back to a central brain during operation.
Exactly. And that decentralized execution is absolutely crucial. It makes the system scalable. You can add more agents without bogging everything down, and it ensures really fast, real-time responses on the factory floor.
That's fascinating. Train together, run independently. So it's like building these super smart self-adjusting systems.
Right.
But how do they actually fit into a company's existing tech?
Yeah.
The mix of old machines, new sensors, different software.
That's a really critical point. Integration, it's key. For MARL to actually work in the real world, it needs to connect smoothly with what's already there. The agents need data from your manufacturing execution systems, MES, from sensors, production databases. That's their perception.
Right, they need the inputs.
And then they need to send commands to actuators, maybe other software systems. That's the control layer. This often means you need some kind of middleware or maybe edge computing devices to handle all that information exchange reliably and quickly.
Edge computing. So the intelligence is closer to the machines themselves.
Often, yes. An agent for a robot station might run on an industrial PC right there, taking in sensor data, sending control signals, and coordinating with its neighbors without massive delays.
And you mentioned digital twins earlier. How vital are they?
Incredibly important. These virtual replicas of the physical systems provide a safe, high-fidelity sandbox. It's where you can train and test the MARL agents extensively without messing up real production. You can try out different strategies, let them learn how to optimize processes, prevent downtime.
All virtually.
All virtually. Then once you've got policies that work well in the twin, you can deploy them to the actual equipment with much higher confidence. So yeah, MRL architecture in manufacturing really blends these advanced AI algorithms with the industrial Internet of Things, often using that centralized learning, decentralized control idea, and heavily relying on good digital twins.
Okay, we've covered the what and the how. Let's talk bottom line. What does this all mean for the business? What are the tangible, real-world advantages companies are actually seeing when they implement MARL?
Right, the benefits. And they are compelling and, thankfully, often quantifiable. Let's start with operational efficiency and throughput. MRL agents are just really good at fine-tuning processes, finding and eliminating those hidden bottlenecks. We've seen case studies. One example, a deep reinforcement learning agent used for scheduling in an automotive parts assembly line. It boosted average throughput by 24.2% compared to the standard methods.
24%, that's huge.
It really is. Another one. In multi-stage manufacturing, using integrated MARL control schemes led to a 15 to 16% increase in the total yield of quality products. The core insight here for you as an executive is that MRL can fundamentally shift your factory from just reacting to problems to actively self-optimizing, building resilience right into your operations.
Those are impressive numbers. But I can imagine some listeners thinking, okay, sounds great, maybe too great. What's the catch? Or maybe, what's the biggest pitfall an executive might overlook when they see these kinds of double-digit improvements?
That's a fair question. A huge pitfall is getting the reward function wrong. You have to be so careful about what you tell the AI to optimize for. If you set up the reward just to maximize speed, for instance, the agents might learn to do that, but maybe they sacrifice quality or use way too much energy or wear out the machines faster.
Ah, so they'll game the system if you're not specific enough about the real goal. Exactly. It's a bit of an art form, aligning the AI's learning goals perfectly with your overall business objectives, not just hitting one specific metric. But back to the benefits. Next up is waste reduction and quality improvement. Because MRL systems coordinate across the line, they can minimize scrap, energy waste, defects. BMW, for instance, used AI vision systems, likely with some coordination logic, and cut vehicle inspection defect rates by 30% within a year.
30% fewer defects.
Yeah. And in semiconductor manufacturing, companies like Samsung have used multi-agent models to cut customer return rates by about 31%. That means less scrap, less rework, lower warranty costs, real savings.
Okay, efficiency, quality. What about handling disruptions? Things breaking down, demand suddenly changing.
That's where adaptive and resilient operations come in. MARL agents continuously learn and adapt. They offer incredible flexibility. There was an assembly line MARL system that dynamically adjusted robot task sequences when things changed in real time. It cut downtime by over 15% just by cleverly reassigning tasks on the fly.
So it makes the whole operation less brittle.
Much less brittle. More immune to disruptions, whether it's machine breakdowns or sudden shifts in demand or supply.
And this all adds up to cost savings.
Absolutely. Cost savings and ROI. AI-driven optimization in supply chains, which often involves MARL for coordination, has shown roughly 20% reductions in logistics costs for companies that got in early. And while it's not strictly manufacturing, think about Google using AI agents to cut their data center cooling energy use by 40%. That shows the potential for energy savings in factories, too, HVAC, compressed air, etc.
40% is massive.
It is. The overall picture is that investments in this kind of AI optimization, including MRL, can yield significant returns. We're talking maybe $2 to $4 back for every $1 invested. Payback periods, often within just 1 or 2 years. So MRL isn't just a tech project, it's a serious investment with potentially rapid and high returns.
Investment, not just a cost center.
Got it. And finally, there's strategic agility and innovation. MRL enables new ways of operating. Think dynamic mass customization, making lot size 1 production a single unique item actually efficient. It also facilitates those dark factories, highly automated, minimal human oversight. This lets manufacturers respond much faster to market shifts, and manufacturers see this. A survey showed 49% view efficiency and flexibility as the top benefits of AI adoption. MRL hits both of those squarely.
Those are definitely compelling arguments for the why. Let's try and bring this to life even more. Can you share some specific, concrete examples? Where are we seeing MRL making a difference right now in different industries? What's actually proving possible today?
Sure, we're seeing really impressive applications, proving this isn't just theory anymore. In automotive, for example, on adaptive robotic assembly lines, leading car makers have run pilots using MRL for things like body-in-white assembly, coordinating welding robots, part feeders, getting them to dynamically adjust their timing. The results: over 15% improvement in output in some cases, plus reduced downtime because the system learns to anticipate and compensate for those tiny micro-stoppages before they cascade.
Preventing the small hiccups from becoming big jams.
Exactly. Then in electronics manufacturing, for intelligent quality control, think PCB assembly. Agents can monitor quality in real time and then adjust the settings of machines upstream to prevent defects from happening in the first place.
Proactive, not just reactive quality control.
Precisely. We mentioned Samsung before achieving that 31% reduction in customer return rates for semiconductors using multi-stage AI, and BMW's 30% cut in inspection defects with their AI vision systems. It's about closing the loop faster.
Makes sense. What about supply chains? Pharmaceuticals, maybe?
Yes, supply chain and logistics optimization is a big one, especially in pharma where traceability and conditions are critical. MARL agents can represent factories, distribution hubs, even transport links. They learn to collaboratively route shipments, manage inventory across the network. Companies using this have reported around 20% cost reductions in logistics. The agents get good at anticipating demand spikes and redistributing stock before there's a problem. It's optimizing the whole system.
Systemic optimization. I like that. What about maintenance?
Predictive maintenance and equipment coordination. This applies pretty much everywhere. Imagine coordinating the maintenance schedules for dozens of pumps and compressors in a plant. One petrochemical facility did this using MARL agents and achieved 0 unplanned downtime for months.
0 unplanned downtime. That's the dream for many ops managers.
It really is. Another cool example, Microsoft's Project Bonsai platform worked with Siemens. They used deep reinforcement learning to tune a CNC machine 30 times faster than a human expert could.
30 times faster,
Right.
drastically cutting setup time, boosting productivity.
Absolutely. And finally, let's not forget warehouse automation, multi-robot coordination. MRL algorithms help teams of warehouse robots complete tasks like order picking much faster. One study showed about a 15% improvement in order throughput when MRL optimized the robot's routes compared to simpler rules. This includes complex things like mixed palletizing, multiple robot arms, figuring out how to share the work so all pallets finish around the same time.
Okay, it's clear MRL is incredibly versatile. These successes aren't just, one-off experiments. There's setting benchmarks, right? Showing what's possible and highlighting best practices, like you said, using simulations and having really clear business goals.
Exactly. These aren't just isolated lab results anymore. They show that if you approach it right, invest in good simulations, really nail down those reward functions to reflect true business goals, this tech is ready and delivers real value.
It really does sound incredibly promising. But let's be realistic. No big technological leap comes without its challenges, its hurdles. So for the executive listening right now, what are the biggest challenges? What do manufacturers need to be really aware of when they start thinking about MRL? Where are the potential tripwires?
That's a crucial question, absolutely, because it's not plug and play. One of the biggest hurdles is simply the technical complexity and stability. Training multiple agents at the same time is just inherently harder than training one. You run into issues like non-stationarity.
Non-stationarity, meaning things keep changing.
Yeah, because as each agent learns and changes its strategy, the environment effectively changes for all the other agents. It can make the learning process unstable, sometimes difficult to get them to converge on a good solution. It often takes a lot of computational power and simulation time, millions, maybe billions of time steps to train these systems effectively.
Okay, complex and resource-intensive to train. What else?
Then there are the data and simulation requirements. We talked about digital twins. Creating a high-fidelity one that accurately reflects your real factory, that's not trivial. If your simulation is too simple, you hit the reality gap. Agents work great in the simulation, but flop in the real world.
The sim-to-real problem.
Exactly. And equally challenging, as we touched on, is defining that reward function perfectly. Get it slightly wrong, and the agents might learn to do something completely counterproductive, even while maximizing their score. You need deep domain expertise here.
Right, aligning the reward with the real intent.
Precisely. Then there's integration with legacy systems. This is a huge one for many manufacturers. Most factories are a mix of old and new tech, different protocols. A recent survey actually found 44% of manufacturers cited integration issues as a major barrier to AI adoption generally. Getting everything talking reliably with low latency, it's a real technical challenge.
44%, that's significant.
It is, and related to complexity is scalability and generalization. Many MRL algorithms work okay for, say, 5 or 10 agents, but scaling up to coordinate hundreds or thousands, which you might need in a large facility or supply chain, that's still an active area of research. The complexity can explode. Plus, agents can be brittle. Train them on one product mix, and they might struggle if that mix suddenly changes drastically unless you specifically train them for that kind of variance.
So they might not generalize well outside their training data.
Sometimes, yes. Needs careful design. And finally, a big one. Transparency and explainability, or the lack thereof. MRL policies, especially the ones using deep neural networks, often act like black boxes. It's hard to know exactly why an agent made a specific decision.
And that's a problem for trust, debugging safety.
Absolutely, especially in regulated industries or safety-critical applications, engineers and operators need to trust the system, and that's harder when it's opaque. This also ties into workforce and organizational challenges. You might face resistance from workers worried about job displacement. It definitely requires reskilling people, maybe shifting roles towards overseeing the AI, managing the systems, and carefully figuring out that human-AI relationship, maybe starting with a human-in-the-loop model where people approve key AI decisions.
Okay, those are substantial challenges: technical, data, integration, scale, transparency, and the human element. Quite a list. So putting it all together for you, the executive listening right now, trying to balance the ambition with the reality, what are the key strategic implications? How do you navigate this complex terrain successfully?
Okay, strategically. First, recognize that MARL offers a significant strategic advantage and is likely becoming a competitive necessity. Companies that master AI optimization, including RLL, will likely achieve lower costs, faster innovation, greater flexibility, they'll build stronger margins. It's widely believed AI will define the next era of manufacturing winners. Something like 93% of leaders see AI as key to growth. So inaction is risky.
It's moving from nice to have to need to have.
Pretty much. Second, regarding ROI and investment, yes, MARL projects need upfront investment in talent, data infrastructure, simulation tools. But the potential ROI is very high, as we discussed, with payback often in just 1-2 years. When building the business case, quantify everything. Direct savings, labor, energy waste, throughput gains, but also the harder to measure benefits like agility and faster time to market.
Focus on the total value proposition.
Exactly. Third, organizational readiness and change management are absolutely vital. You can't just drop this tech in. You need to actively champion a culture where humans and AI collaborate. set up cross-functional teams, provide training so engineers and supervisors understand how to work with these systems, interpret their outputs, define clear governance. What decisions can AI make alone? When is human oversight needed?
Building the human infrastructure alongside the tech.
Couldn't have said it better. Fourth, technology integration and data infrastructure are foundational. You need robust data collection, think IoT sensors. You probably need good digital twin capabilities. And that requires strong collaboration between your IT teams managing data networks and your OT teams managing the physical machinery. They need to work hand in glove. Plus, cybersecurity becomes even more critical.
IT-OT convergence is key here.
Definitely. Fifth, adopt an adoption roadmap and pilot strategy. Don't try to boil the ocean. Approach MARL in phases. Maybe start by exploring its potential in simulation, then pilot it on a limited, well-defined scope in your actual operations. Measure carefully. Then, if successful, plan how to scale it out and involve your end users, the operators and engineers from the very beginning. Their expertise is invaluable.
Start small, prove value, then scale. Sensible.
And lastly, think about collaboration and the ecosystem. You don't have to do it all alone. Consider partnering with tech providers, universities, maybe industry consortia. This can de-risk the investment, give you access to specialized expertise and talent, and keep you at the forefront of what's possible.
Leverage the ecosystem. That's a great strategic framework. Okay, looking further out now, say the next 3 to 5 years, maybe even towards 2030. What's next for MARL in manufacturing? Where is this all heading?
Well, if we extrapolate the trends, we can anticipate wider deployment of fully autonomous factories, or at least production lines. That idea of the lights-out factory with minimal human intervention, it moves closer to reality, especially where labor costs are high or tasks are hazardous. By 2030, expect many new factories to be designed with AI, managed by intelligent agents at their core.
A fundamental shift in factory design.
Potentially, yes. We'll also see deeper integration with other emerging technologies. Think IoT and 5G, providing even richer, faster data streams for the agents. Think hybrid edge and cloud computing, heavy training in the cloud, super fast decision-making right on the machine edge, millisecond responses.
Taking advantage of connectivity and computing power.
Exactly. And digital twins will become even more sophisticated, allowing companies to basically rehearse complex MRL-managed operations entirely in simulation, dramatically cutting risks for things like commissioning new lines.
More virtual testing, less real-world disruption.
Right. Another big trend is AI convergence. MARL won't be siloed, it'll merge with computer vision so agents can literally say what's happening. Maybe they'll use large language models to understand instructions or communicate issues more naturally, and federated learning could allow multiple factories, maybe even across companies, to collaboratively improve MARL policies without sharing sensitive raw data.
Learning together while maintaining privacy. Interesting.
Very powerful. This convergence enables new applications and business models. Truly efficient mass customization, that lot size 1 dream, becomes much more feasible because MRL can handle the immense scheduling complexity. We could see real-time coordination across networks of factories for global optimization. Maybe even automated maintenance marketplaces where a machine's agent detects a pending failure and automatically orders the right part from a supplier's agent.
Wow, agents doing business with other agents.
It sounds futuristic, but the building blocks are falling into place. And crucially, human-agent collaboration interfaces will get better. Think augmented reality overlays showing operators what the AI is planning, or natural language interfaces to query the system, making it easier for humans to work alongside, understand, and trust these complex systems.
Improving the human-AI teamwork.
Yes, and ultimately, MRL systems might lead to surprising emergent behaviors and incredible resilience. Agents could discover novel, super-efficient ways of organizing production that no human ever thought of. And they could make factories extraordinarily resilient to shocks, automatically rerouting production around a broken machine or a delayed supply shipment in incredibly complex and effective ways.
So the manufacturing sector, which some might see as, traditional, it's really on the cusp of a massive AI-driven transformation. And it sounds like multi-agent reinforcement learning is right at the heart of this evolution, moving beyond just tweaking things to fundamentally changing how factories operate.
That's exactly right. Multi-agent reinforcement learning is rapidly becoming a cornerstone, really, of this next industrial revolution. When you harness it effectively, it drives improvements in throughput, in quality, and responsiveness that go well beyond what traditional automation or even single-point AI solutions can achieve. The benefits for companies that navigate this journey successfully, they're substantial. We're talking potential for cost leadership, much greater greater agility, real competitive separation.
The coming years certainly sound pivotal. It feels like by 2030, the gap between manufacturers who've embraced AI augmentation and those who haven't could be as stark as the difference between automated and manual production was decades ago. Acting now really could secure your place on the right side of that divide.
Couldn't agree more. The time to strategize and start exploring is definitely now.
Thank you for joining the podcast, and see you soon.
Thank you for joining the podcast, and see you soon.